So far we've seen that if you know that a function is continuous, that is quite helpful in taking limits at any point. This is actually at the very top of my list, David's list to taking limits. Meaning if a function is continuous, and many functions are, all you have to do is you plug in and you get the limit out. Now, in many cases, and specifically in exams, in worksheets, and in practice questions, when you plug in, you'll get something that is undefined. For example, 0 over 0, or infinity over infinity. Or sometimes things which are undefined because they contain cosine of x going to infinity, for example. Now, this list covers all the basics and the things that you should try to solve limits. And it's ranked in terms of kind of how complex or how much work it is going to be to take the limit. So you should always try with something that's easy and quick, and then move along to something that is a little bit more complicated. If you practice, you will be able to actually recognize almost straight away in which cases you should be factorizing an expression, in which cases you should be dividing by the highest power, multiplying and dividing by a conjugate, or the cases where you're going to use the squeeze theorem. But let's go back a little bit in time, remove this, and actually go through the lists with a little bit of physics 101 magic. Now, if you want to take a limit of a given function, say f of x, and you want to calculate the limit when x goes to a of f of x, this list helps you, especially if you've never taken limits before, it helps you navigate the things you definitely should be trying, and that will lead to success in physics 101.
That's correct.
So number one, first thing you should do is sub in. As I've mentioned already, a lot of functions are continuous at the point that you're looking at, which means that if you sub in, you get the limit. Remember, for a function to be continuous, its limit needs to equal the value of the function at that point. That's why this will work. In many cases, this will not be the case. You may end up with something that looks like 0 over 0. In those cases, one of the things you can try, and we already saw in a previous example, is to actually factorize the expression. This means re-expressing it in another way. Factorizing will help because you can take an expression and factorize it into 2, sometimes 3 or 4, and hopefully you'll get a term that will cancel out the denominator. This means you will no longer have a 0 over 0, and then you can revert to number 1. By subbing in, you solve the limit. In other cases, you will actually have something that looks like infinity over infinity, and this could be plus or minus. In these cases, it typically means you're maybe taking x to infinity, or the numerator and denominator are both going to infinity. The way to deal with it is, from an intuition point of view, it's to understand which component is going to infinity quicker. And you may be able to realize that, and perhaps you already have the intuition, or you've plugged it in into a calculator or a computer, and you will be able to solve these limits kind of straight away. The important thing is you can't just give that answer and saying it's because it's obvious. You need to show it. And a very neat, simple way to show it is to divide by the highest power. To divide by the highest power, this typically means that all the other terms will be going to 0, and the highest power will prevail, essentially. And this will be really useful, again, for limits of infinity over infinity, and you will break this indetermination. In other cases, you also have something like 0 over 0, sometimes even infinity over infinity. But factorizing doesn't really work, and you can't really cancel the terms. Sometimes it involves something like square root of x, or something on those lines. In those cases, it actually helps to multiply and divide by a conjugate. It's probably been a while since you've done some maths. That's okay. So if you need a quick recap of what a conjugate is, it is incredibly simple. So if you have something that is the form of a plus b, the conjugate is simply a minus b. So what I'm suggesting is, as number 4, if you have something in the form of 0 over 0, especially if you have square roots of x, it really helps if you try to multiply and divide. It means you're multiplying the numerator and the denominator, so it cancels out. You're not really doing anything to the expression. And if you expand that, typically it helps you getting rid of the denominator if it's going to 0. And again, you achieve something very similar to number 2. Unfortunately, it is possible that after trying all this, you're still kind of stuck and you still have something that is undefined. In those cases, it's really, really important to go back to the properties of limits, which we have covered, and to try to manipulate the expression, realizing, for example, as we've covered, that the limit of the product is a product of the limits, or that the limit of the sum is a sum of the limits. This means number 5 is all about trying to break the limit into parts where you will be able to calculate the limit for. So maybe you don't know the limit of the entire thing, but if you start breaking it apart, it becomes easier. So that's what number 5 is all about. By re-expressing the limit, you will be able to calculate the individual parcels of it and then sum them or multiply them or divide them to get the final result. This number 5 is actually really crucial, and this is how we're going to prove a lot of differentiation rules by exploring the properties of limits. So if you don't remember or you skipped that video or that section, go back to the properties of limits, which you will be able to find in section 3.4 of the lecture notes. Finally, especially when you're dealing with trigonometric functions and you're taking something in the expression that involves a sine or a cosine to say infinity, or part of what's contained within the sine is going to infinity, that really has no meaning, but the overall function may be actually tending to a specific value. A very neat way to prove that is by using something that we will cover, which is called the squeeze theorem. The squeeze theorem essentially tells you that if you can find two functions that bracket the function you're trying to find the limit to, and if you can take or know the limit of those functions at the point that you care about, then you know how to calculate the limit of your function. And this may seem a little bit weird and strange, but we will define it in a very rigorous way mathematically. And also I'll show you examples where you can actually use it without even thinking that you're exploring the squeeze theorem. As an extra step, some of you may have heard about L'Hopital's rule. This is not part of my list, and the reasons are also fully explained in the lecture notes. That is because L'Hopital's rule is really useful to solve limits, but it relies already on you knowing how to differentiate. Now, the way that I'm setting up Physics 101 is to have some proper mathematical rigor, and we will use limits and the way we calculate limits to actually define what a derivative is and to calculate them from first principles. So you'd see that it would look a little bit weird if we're already using differentiation rules to solve limits and then using limits to prove those differentiation rules. So I'm not going to do it, but it means that if you've covered L'Hopital's rule before, you know how to use it, and I've also included actually just the conditions where it is valid on the lecture notes. You are welcome to use them. I would, however, encourage you to use this list even if you know how to use L'Hopital's rule, because it makes things much more self-consistent. Once we derive differentiation rules at the end of the module, then I would say it makes sense to use L'Hopital's rule to solve limits. Until then, not really. In the next sections, in the lecture notes and in the videos, we'll go through examples of the different methods so you know in practice how to use them, and I will try to highlight any small tricks or definitions that you may need to use.